Hello, Merry Christmas. The goal of this video is to show you an example of the bonding assignment that we just did. So that was bonding assignment 1, in which you were given a molecule. You had to identify the polarity, predict the shape, and use those things together to predict chemical properties. I'll go through 2 examples. I'm going to go through methanol, which is CH3OH, and then I'll go through another carbon molecule, in this case C2H6. So CH3OH. So the way to start is to try to figure out how many bonds each element makes, and this information you have already. But if you didn't, one thing that you can do is look at the group each element is in. Carbon's in group 4, hydrogen is in group 1, and then oxygen is in group 6. Excuse me. So what that tells you is that carbon has 4 electrons in its valence shell. Group number tells you number of valence shell electrons. It also tells you how many bonds it's going to make, because remember that most of the elements are trying to fill up the valence shell, and they can do that by ionic bonding or by sharing electrons, which is covalent bonding. And covalent bonding is the type that carbon does. And so it's actually going to make 4 covalent bonds. So it's going to share each of its 4 electrons with 4 more electrons to make 4 covalent bonds and fill its valence shell. So first sketch, well, I know that it's going to have 4 lines coming off it. I know that hydrogen is in group 1. It's got 1 valence shell electron, so it needs 1 more to fill that shell. It doesn't have 8, or it doesn't have the, only has 1 electron shell, which holds 2 electrons, because it only has an atomic number of 1. So it only makes 1 bond. So I'm going to fill up some of the hydrogens, just to get a rough idea of what this molecule really looks like. I know that oxygen is in group 6, so the same trend of number of valence shell electrons and the group number telling you how many bonds it needs to make is true in this case as well. Oxygen's in group 6, so it needs 2 valence shell electrons to complete its shell, so 2 covalent bonds. So oxygen will probably have 2 lines coming off it, or 2 bonds. I'm not really sure of the shape or anything else yet. All I'm doing now is just getting a rough idea of what this thing looks like. So my next step is to think about the polarity. I know that I've got 3 separate bond types in this molecule. So carbon and hydrogen, this is the same as this and this. Oxygen and carbon bond, and then an oxygen-hydrogen bond. So what I need to do now is use electronegativity values from the periodic table, subtract the biggest from the smallest. In this case it's carbon, which is biggest. Excuse me. So carbon minus hydrogen gives you 0.4. Oxygen is 3.5 minus 2.5. 1.0. Oxygen hydrogen is 3.5 minus 2.1, 1.4. So slightly polar, it's just in the threshold of being polar, so all the bonds are polar. So what I need to do now is label delta positive, delta negative charges. So the biggest, or the element with the biggest electronegativity value will be delta negative. So I'm going to leave carbon, oh actually no, I'm going to label it for now. All the hydrogens though are delta positive. Electrons being drawn in towards the carbon. Oxygen is the biggest, so that will be delta negative. And that carbon here has a delta negative and a delta positive charge, so they cancel out. Okay. So this bond, electrons being pulled this way, and this bond, the electrons are being pulled this way as well. So that's delta positive. I should also add lone pairs of electrons here. So I've got the polarity. So I know that there's an area of potential delta negative charge and delta positive charge, so could be polar. What I'm going to do now is actually redraw this to show a 3D version. If you remember the models that we work with, carbon makes like a kind of a tripod shape with a bond sticking up. So this would be the bond that's coming out towards you. This is the bond that's going back into the board, and these are the two bonds in the same plane. Still not sure of what I'm going to do with this yet, but right now I'm going to take a guess that maybe it's polar, right? But what I need to do now is to confirm that is to look at the shape. So there's no more. Oh. So I'm going to erase this now. And I know that I've got two bonded pairs, two lone pairs. So the lone pair repulsion here is stronger than the repulsion between these two bonded pairs. And VS EPR theory states that the lone pair repulsion is the strongest, then it goes lone pair, bonded pair, then it's bonded pair, bonded pair. So however you chose to say it in your video, there's slightly different ways to actually say it. The arrangement with the least, that takes the least amount of energy, is for the bonded pair and bonded pair to go next to each other in this arrangement. And the lone pair is the strongest. And so they could push these bonds together. These bonds have the least repulsion, so they end up being next to each other. So rather than this shape, because of the lone pair repulsion, it's actually this arrangement that forms. And you can think of the main reason why is that these two bonds, it takes the least amount of energy for these two to go together this way. And it's the path of least resistance in most cases, so that will be the arrangement that forms. So actually we'll leave that up because this is actually kind of a tetrahedral shape. So if you imagine, if I redrew this, so this is this bond, kind of redrawn. These are lone pairs. I can actually, let's pretend, just for fun, that these are actually two bonds. They aren't, obviously, because they're lone pairs, but just to get the idea of the shape, these lone pairs do kind of make a tetrahedral, but they repel each other more, so they're pushing these bonds down to make this a reduced tetrahedral. If this was a tetrahedral, it'd be 109.5 degrees, but because this repulsion is stronger, it actually ends up being less. 104.5 degrees, or the bent shape. So I've used VSEPR theory to state that because of the two lone pairs on oxygen, it makes the bonded pairs line up next to each other, and actually it's a reduced tetrahedral shape. I'm going to erase this now. To look at carbon, to use VSEPR theory, the number of electron areas is 1, 2, 3, 4. So that's 4 areas where electrons are. There's 4 bonded pairs, 0 lone pairs. The only shape that it can be is a tetrahedral. So these bond angles would all be 109.5. I've already talked about this, but this is my bent shape. So this is a bent shape right here, and this will be tetrahedral on this part. So this would be a tetrahedral portion of this molecule, and this would be the bent shape. So there's really 2 shapes in that. So even though I've redrawn this, this bond angle here, because this makes it much more obvious that it's actually going to be a polar molecule, because there's now this area that can attract another delta positive part of another molecule. So if you imagine a sample of methanol, a liquid, which I'll talk about in a second, but it can attract other molecules through this interaction between delta negative oxygen and a delta positive hydrogen. Alright, so because of this, because of its shape, which exposes this delta negative part, and because of its polarity, it is a polar molecule. So the bonds are all polar, and because of its arrangement and its shape, it's also a polar molecule. So because of this interaction, you can actually predict that this would maybe be a liquid, at room temperature. Remember that molecules that stick together more easily like this, that are polar, usually, not always, there are plenty of exceptions, but usually make a liquid. And so what I would actually do now is do a Google search to confirm that. So my prediction is that it's a liquid, and actually it is a liquid at room temperature. Other evidence that helps support that is the fact that all the elements that make up methanol are actually quite light. So oxygen has and carbon, and actually the hydrogens, it doesn't have a particularly heavy mass compared to some of the molecules. So that would lean towards it not being a solid, but this polarity though, because these bonds are actually very polar here, this is definitely evidence that it will be a liquid at room temperature. So the sketch that you'd include in your submission would actually have the calculations for polarity, which I erased, but basically you'd include all this. So the sketch needing to include the shape of the molecule correctly drawn. This includes two shapes, here and here. The bond angles, the names of the shapes, delta negative, delta positive charges, lone pairs of electrons, and that's it. So for methanol, I'll go through this molecule next, which is ethane. But this was the level of sketch that you needed. Didn't need to be a lot, just needed to be quite brief, but making sure everything was included. So erase all of this. Okay, so same procedure with this molecule, which is ethane. Alright, so I'm not sure of the shape yet, but let's just use what we talked about for the last molecule. I know that carbon makes 4 bonds, it's going to have 4 lines, each one is going to have 4 lines coming off it, and hydrogen only makes 1. So, still not sure of the shape. So there's 2 carbons and 6 hydrogens, and hydrogen only makes 1 bond, so there's no way that I can have 2 lines coming off hydrogen. The only option is for carbons to have 2 lines coming off it. So I'm still trying to figure this out. I don't know if I've got this correct yet, but I've got 6 hydrogens to fill in 1, 2, 3, 4, 5, 6 spots. And ooh, that's nice. How convenient. Right, so C2, 2 carbons, 6 hydrogens. Each carbon makes 4 bonds, each hydrogen makes 1. Nice. So what I'm going to do next is look at, because I know how to do this now, I've gone through this, I'm actually going to redraw this in 3D. So that would be my, so I've got 2 in the same plane. This could be the one that's coming out. So I've redrawn it in 3D, which is a more correct way to represent this molecule. I've only got one type of bond. This is going to be 0 polarity. Carbon and carbon is going to be non-polar. And then carbon-hydrogen is 2.5 minus 2.1. So that is slightly polar. So the bonds are polar. So what I need to do now is label delta negative, delta positive. So carbon would be delta negative. And that makes all the hydrogens delta plus. So a good thing here to do, if you're still not sure of whether this is a polar molecule or not, is make the actual model using the models that we have in the lab. So, but just looking at it though, you've got delta positive charge all the way around this molecule. So makes the molecule non-polar. There's no negative end and positive end. So the molecule is non-polar, even though the bonds are slightly polar, but it's a non-polar molecule. So I'll need that information when I talk about chemical properties. What I'm going to do now, though, is talk about the shape. So it's easier just to look at each carbon on its own, first of all, knowing in your mind that each carbon's identical. So whatever this shape is, this one's going to be the same. So there's 4 electron areas, 4 places where the electrons are. 0 lone pairs, because this is 2, 4, 6, 8 around this carbon. So 0 lone pairs, 4 bonded pairs, 4 electron areas, there's only one shape, and it's a tetrahedral. So this bond angle will be 109.5 degrees. The shape is tetrahedral. And because this section of this molecule is identical to this one, I'm just going to put an S right there, because whatever this is, this has to be the same. So this is 2 tetrahedrals added together, if you will, or joined together. So still nonpolar. So chemical properties. Again, a Google search will tell you, but in your video, you could predict that because of this non-polar molecule, because it's light enough, 2 carbons is pretty light, and the hydrogens are obviously very light, they only have an atomic mass of around 1. So my prediction is that this is going to be a gas at room temperature and pressure, because non-polar, so one molecule will not probably interact with another one that easily, because as they come together, the light charges are going to repel the delta positive light charges, which are all around the outside. So probably non-polar. And actually ethane is a gas at room temperature and pressure. The shape of it means that there's no negative delta positive end. The polarity obviously tells you that it's a non-polar molecule. So a gas at room temperature and pressure, not very reactive based on that. And I didn't mention about methanol, that it can be somewhat reactive because the polar bond between the oxygen and hydrogen can actually break quite easily because the electrons get drawn to the oxygen a lot more readily. So methanol is more reactive. It's used in fuel, some fuel. If you've seen Fast and the Furious, it's used in that as a fuel injection type thing, whatever that means. But you can react things with methanol quite easily. Ethane, though, not quite as reactive. Non-polar, the shape dictates that there's no negative positive end. And all the bonds are slightly polar, not very polar. So there you have it, you've got 2 molecules. Tried to show you what the video would include, a description of VSEPR theory, which tells you what shape it will have. Polarity also helps you understand some of the chemical properties, as well as adding in the information about shape. So all these things come together to give you an idea of why certain molecules behave the way that they do. The sketch for this would include, I guess, all this. That's all you needed to do. So that's it.